Hello everyone. Myself Dr. Rajesh Prasad. I am currently working as professor in Ajay Kumar Garg Engineering College, Ghaziabad. So today I am going to discuss one of the important topic, traveling salesman problem. As we know that this is like NP hard category of the problem. It is not easily solvable. So we'll try to give multiple solutions to this. So today I'm going to explore the dynamic programming approach to solve the TSP problems. Okay. So we'll see that how TSP is going to solve, and then we'll look at approximation solution of the particular problems. Okay. So actually let us understand. So what is TSP? You know, so in this TSP, a set of some cities are given. Like we can assume that if you model this problem using graph, we assume that set of cities are denoted by the nodes, right? So set of cities are given, okay. And second thing which is given as the distance between every pair of cities, right? So these are the input. Cities are given, and there is connection distance between these two cities are also mentioned. Of course, these distances, they are going to be positive, right? Yes. So TSP actually states that a salesman has to visit every city exactly once, right? So you know, objective of this salesman is that it has to like visit every city exactly once, right? And no city should be repeated. Number one. Number two, he has to come back to the city from where he starts his journey, right? So suppose if a salesperson is starting from number one, going through multiple cities, many cities are there, all of them are interconnected, right? All of them, they are interconnected. Okay. So, but ultimately he has to come back from where he has started, right? So, and so question is that what is the shortest possible route that the salesman must follow to complete his tour? That is the objective of the problem. So you know that salesperson, if it is starting from a particular node and visiting every vertices exactly once and coming back to the number one, right? Same vertex, and but cost of the travel should be optimum. Optimum in the sense is minimum. Remember, vertices can be visited exactly once, while edges can be visited more than once. There is no restriction on the edge, but there is restriction on the vertex. One vertex can visit every at exactly once, and we have to visit all the vertices also. Okay. So for example, let's understand this. Suppose we have cities A, B, C, D. Like we have 4 cities over here, right? And distance between each city is also mentioned. If suppose a city is not connected, then we can assume that distance between directly connected, then distance between them is infinity. This, it is possible that one city may not be directly connected to other city. So you see here the like if we salesman starts from city A. Suppose a salesman is starting from city A, clear? Then a TSP tour in the graph could be like A to B. A to B, if you go, it is 10, right? And B to D, B to D is 25. D to C, D to C is 30. This is the cost weighted graph is given, and then C to A is 15. Ultimately, you have to come back from where you started, right? So cost of this is 80. And remember, it is not necessary that this cost is the optimum cost. It may be like there may be another exploration which can give the lower cost than 80. So objective is to minimize this cost, right? So there are many solutions. One of the solution is the dynamic programming. You remember dynamic programming approach to solve the TSP problem. We know that dynamic programming and DP and greedy, they are the optimization problems. And we know that in dynamic programming, we are going to get exactly one solution. And this is working from the bottom to top. Okay, and greedy, we are getting multiple solution and we are just choosing the best among these solutions. So greedy solution for this TSP is not existing. Okay, and only dynamic, branch and bound and approximation solutions are existing. So what, let's see what are the steps in dynamic programming. We know that there are 4 major steps in the dynamic programming. Okay, number one is the characterize the structure of an optimal solution. While characterizing the structure of an optimal solution, we should always make sure that principle of optimality is always holding, right? Principle of optimality is always holding. That means if you are going from I to J, okay, going from I to J via K, okay, so this is not, if this is not the direct path, so definitely there is shortest path K, such that you can go from I to K and then K to J. So optimality principle is saying that if you are choosing any alternative path, so this is also optimal, this is also optimal, right? If this is not optimal, means there is another path which you can follow. So this is not going to be the shortest, there is shorter than this. So, you have to choose this structure of an optimal solution such that principle of optimality is holding. Okay. After choosing the characteristics of the problem, number one, number two, you have to define the solution, recursively define the value of an optimal solution. How solution will look like, as I told you that, okay, this dynamic is always working from bottom to top. It's not working from top to down. So you have to use the recursion to look into the solution of the problems. Then third number is the compute the value of an optimal solution. Here in the TSP, it will be given like, okay, what is cost of the optimal salesperson tour, right? So this is going to be computed into third step. In fourth step, you have to construct the solution based on solution such that its cost is going to be this cost actually. The fourth step is just giving the solution from the computed information. So let's apply this DP approach on the TSP problems, right? Okay. So this is the assumptions. This is the assumption that we are assuming that G is a graph, okay, having V vertices and E edges, be a directed graph. Here we are taking directed graph. We are not taking undirected graph, right? With edge cost Cij. We assume that this edge cost Cij and this is of course going to be greater than 0. We are not interested in 0 cost, right? For every I and j. This is first assumption. Okay, and now Cij infinity if Ij is not part of the edge. If Ij there is no edge, that means Cij will be infinity. And we also assume that number of vertices are n. N is greater than 1. Minimum 2 vertices are needed. Okay. So let us define a tour. Tour is nothing but is like a cycle that include every vertex in one. And so the cost of a tour is the sum of the cost of the edges on the tour. So the TSP is to find a tour of minimum cost, right? So you have to include every vertex, remember not edge. Edge can be repeated, but vertex cannot be repeated, right? So we are going to find out the TSP is find out the tour of minimum cost, right? So we are always going to minimize the cost. So we assume here that we are starting from vertex number 1. Okay. So every tour consists of an edge. Of course, if you start from 1, so of course you are going to get the K via K. Starting from 1 via K. Of course, and K can be any other vertex, and finally you have to come back on 1. So for some K belong to V minus 1. Of course, K is not going to include 1. So all the vertices minus 1. And a path from K to 1 also. So this is the next first step. So the path from vertex to vertex 1 goes through each vertex in V1 minus k. Very simple. Suppose we are starting from k, right? 1 and 1 to k. Definitely then k to 1 always. So this is the assumption that if you are starting from 1 going through k, and remember k to 1 also. So from k to 1 you are always coming from v minus, we are not taking 1, and k, that whatever k we have taken, it is going to be excluded also. So let GIS be the, now we are going to understand the formulation by recursion method. Okay. So let GIS be the length of a shortest path starting at vertex I. Okay. Yes. Going through all vertices in S and terminating at vertex number 1. This is the notation. So actually from this assumption, we are going to find out G1 minus V1, right? Start from 1, going through all the vertices of V, not including 1, because we have to come back at 1 always. So is the length of an optimal salesperson. So if you just define this, GV minus 1. Okay, so if you understand, so this we are interested in minimum. K cannot be 1 because we are already excluding 1. So 2 to n, number of vertices. So if we start from 1 to k, right? Yes, because k 2 to n, go through 1 to k. And then from k, you have gone from 1 to k. Then from k to all vertices other than 1 and k. Simple. So this is formula. So like G1 comma, like if you see here, G start from 1 going through all vertices other than 1, right? So definitely this is nothing but minimum k. K cannot be 1. Okay. So this is minimum of this, and go from C1, start from 1, go to k plus, okay, plus G. After going through k, 1 to k, then you have to start from k, and of course all the vertices other than 1 and k. Whichever is coming minimum, that is going to be the path, right? And next assumes first one, second one is very simple, that okay, from all I to, if we are not having any vertices, so of course you have to come back to 1. So that means GI5, we are exhausted with any number of vertices is CI1. Start from I and come back to 1, because this is a tour. Okay. Let's have one example. This is the base formula. This is important formula. It is going to use. So this, let us have this graph. Okay. So 4 vertices are there. 1, 2, 3, 4. And these are 1, 2, 3, 4. This is the actually adjacency matrix path, like we have designed it. So we are assuming that 1 to 1 is nothing. So this is 0, 0, 0. Okay. So this is actually we have computed. 1 to 2 direct is this 10, but it's not necessary that 2 to 1 is also 10, because it is not symmetric. We have taken the directed graph, right? So this is the matrix. Okay. So after computing the matrix, you can withdraw, you can remove this graph. So you know, actually, so based on this formula, if you understand it, what we are going to compute, we have to start from 1, okay, and v minus 1, we have 4 vertices, right? We just exclude 1, so 2, 3, 4 is the option. Again, look at here. We start from 1, v minus 1, like you know, you exclude 1, so it will remain 2, 3, 4. Okay. So this is minimum of k less than or equal to 4, and this is 2, because we are interested in only 4 vertices. Okay. So now C1 1k plus gk comma gk comma v minus 1k, right? So v minus 1k. This is actually the formula. Okay. So if we just break it into steps, like this is actually nothing but minimum. Let us take k equal to 2. So this is 1 2, okay, plus g 2 comma k is 2. So exclude 1 2. So this will be 3 4. Clear? This is 3 4. Look at here again. If you just take k equal to 2, so this will be C12 plus G2, and 1 2 is excluded. So V minus 1 2 means like 3 4. This is the number 1. Second one is C13, okay, plus G3 comma, then 1 3 is excluded, so 2 4. This is the second option. And the third option will be actually C1 4, okay, k can be 4 plus G 4 comma V1 4 is excluded, so this is actually 2 comma 3, 2 comma 3. This is how we are going to compute, okay. So this number 1, this number 2, this number 3. Anyone which is coming minimum, we are going to decide. And now this is recursive procedures, right? So if you start considering this one, now you see you have to compute G2 3 4. See here. Now if you start, in order to get this value, we have to compute this value also. Now G2 comma 3 4, okay. So G2 3 4 is minimum of same thing. Start from 2 going through 3 4. So minimum of k is like we have to exclude this, right? So 3, k can be 3 and 4 here, like you see we start from 2 3. So you see here minimum of C2 3, you go from 2 3 plus G 3, remaining is only 4, okay. This is the first option. Or C2 4 and then G4 and then remaining is like 3. This is the one option, okay. This, so again this is not going to be terminated again, okay. So if you just go G34, okay, so C34 plus G4 comma 5, nothing is included. So C34 plus G4 5 is C41. So now G34 is going to be 12, okay. So this is 12 plus 41 is 8. So this is going to be 20. So this guy 34 is getting 20. This guy is 20, okay. Yes, and 2 3 is 9. So this value is becoming 29. Let us compute one question here. 4 3, G4 3. If you see 3, G4 3, C4 3 plus 3 2 1. So that means C3 1. 4 3 is going to be 9 plus 3 1 is going to be 6. So this is getting 15. So this guy is 15, okay, and 2 4 is 10. So this is like 25. So this minimum value up to 3 4 is 25. This answer is 25. So if you just put it over here, this is 25 and 1 2. 1 2 is 10, okay. This is 10. So making it 35. This value is 35. We got it. This value is 35. Similarly, if you start computing this value also, you will see that same fashion. This will be 40, and if you start computing this value, it will be 43. So minimum value is 35. So that means length of an optimal salesperson tour is 35. Step 3 is computed, right? Now step 4 is saying that, so okay, this 35, so which one is what is the cost, or what is the path of this 35? So in order to get the path of this 35, what you are going to compute, just check the minimum one. So minimum from this one is 35. So this we got from K. k was here 2. That means we start from 1, go via 2. Simple. We are going to discard it. So k is 2. Now compute this guy 2, 3, 4. You see here 2, now 3, 4. So from here you can go to 2, 3 or you can go to 4 directly, right? So 2, 3, 4. Which one was minimum? Minimum was 4. Look at here. This 25, this guy was minimum, not this one. So that means we are getting 4. So 2 to 4 is the next one. So from here you just check 4, 3. Okay. So now check G 4, 3. And 4, 3 of course is going to be the 4 to 3. So that means is only one remains. So 4, 3 to 3. And you can come via 3 to 1. Very simple approach, right? So that means this is the path 1 to 2, 2 to 4, 4 to 3, 3 to 1. So this is the length of, this is the path of optimal salesperson tour. And what is its cost? 35. So this is very simple solution. Here is the rest of the computation. You can check it. That computation like this previous computation. 3 to 4, this is given here. See 3 to 4, this is the one, minimum is 25. All this computation you can verify, there is no problem. So if you start to analyze actually, so analysis is always important over here. In the worst case scenario, the time complexity of the dynamic programming approach is actually going to be factorial, n factorial. Why it is going to be n factorial, right? Because you have to visit every vertices, right? So it depends on one. Rest can be 2, 3, 4, rest can be 4, 3, 2, rest can be 3, 4, 2. So time complexity of the dynamic, TSP using dynamic programming is always going to be n factorial. It is a permutation problem, and we know that n factorial is n to the power n. We go, and this is greater than 2 to the power n. So this time is always going to be exponential in time. Okay, so these are the references. You can go through this Donald note, or you can follow the core man. You will see the references. Thank you for watching.